Hello everyone, welcome to Step 4 2-in-1 class. So far, we have studied on using auxiliary information in the sampling design. Examples include PPS sampling and stratified sampling. In PPS sampling, size measure is the auxiliary information. Stratified sampling, straight-on information is the auxiliary variable. Now, we want to use auxiliary information in the estimation stage. Examples include the ratio estimation and regression estimation. So we'll study ratio estimation first, and regression estimation will be covered next week. Okay, to motivate the ratio estimation, let's consider the two examples that we covered in week 2 lecture. So in a town, there are 4 farms, and the sizes and the yields of the size acres and yield of the crop, a particular crop, is listed in the table. We use this example to illustrate the simple random sampling and the concept of the probability sampling. Now, suppose that the average farm size is known. So what is the average farm size? For the 4 plus 6 plus 6 plus, so and 20 equals the 36 divided by 4, 9, right? So the average farm size is 9. Okay, so that is known, suppose. And now we if we use simple random sampling of size n2, and we end up with first 2 elements as a realized sample, then you can see that the farms acres are 4 and 6. So the average is x bar is 5. Okay, so the population mean, the point is that, okay, we know that on average, the size of farm has average 9 acres, but this particular sample has average 5 acres. So that gives the information. So what would you say about this sample? Okay, so we realize that, okay, the sampled farms are smaller than the average. Smaller. So that gives an information. So that means the sample estimate, which is 2, right? The mean yield from the sample is probably smaller than the truth, smaller than the population mean. So that would something you can think of. And then question is, how can we use this information? So we observe 5, but we know that it is 9, right? So how can we use that information? So let xi be the auxiliary information known with known population mean x bar u, and x bar x bar is the sample mean. So we use this one is population mean. Okay, so without subscript, we will just assume that it is sample, and everything is simple random sampling. So note that the sample underestimate x bar by a factor of x bar over x bar u, right? So in this particular example, that was 9, and this was 5. So the sample is actually this fraction, 5 over 9 fraction of the true mean, right? True mean of the acres. So you may want to multiply. So this is actually the other one, right? The reverse of this factor to the sample. So the ratio estimator is basically compute this factor and then multiply the inverse of this one, because to reflect the underestimation, to overcome the underestimation. So in this two example, we multiply 9/5 to the sample mean. Okay. So in this example, there are 6 possible samples of size 2, right? The first column corresponds to the sample index, index of the sample farms. Second column corresponds to the sample mean of the y values. And third column corresponds to the ratio estimator using x bar u information. So y bar r is x bar u divided by x bar times y bar. Okay. So for example, if sample 1 for 1 and 4 are sampled, then y bar. So because 1 and 4, then we select these two. Okay, we select these two. So so that means x bar. So how can we get this? So 9, right? And then here is 4 plus 20 divided by 2, which is 12, times 8. So that is the 6. Okay. So now using the above table, using this table, under simple random sampling, we actually have a probability, right? So we have a probability, and the probability are all equal on the simple random sampling. So should be 1/6. So using that, we can actually compute the mean and variance. So that is, this one is essentially 1/6, 3.5, 3.6 plus 5.4, 6.92. Okay, is this one. Okay, so that's interesting, because the population mean of y here. So if you, what is this? So that is a 24 divided by 4, which is a 6. Okay, so the average to the mean is 6, but the average of the ratio estimator is not equal to the expectation of the ratio estimator is not equal to 6.0 true mean. So that is, ratio estimator is biased. Okay, and variance, if you you can since this is a random variable, right? So you have a random variable taking these values, so you can actually compute the I don't know, that you can maybe do something like this. Okay, right? So you already have this one, know this one, and this one you can compute 1/6 times 3.6 square plus 5.4 square plus, so you can calculate it, right? And then you end up getting this one. So that means your MSE is variance. So this is a variance of the y bar r, and this is essentially bias and squared. So that actually is not really, it's quite small actually, which is much smaller than the MSE of the sample mean on the simple random sampling. So that so the ratio estimator is quite efficient. I mean, more accurate than the simple mean in this example.